Hey everyone, I'm excited to share this interactive MRI simulation with you. As you can see on the screen, the left side shows a proton spin simulation, and the right side displays the resulting MRI image. You can adjust the magnetic field strength and RF pulse intensity to see how it affects the image. Feel free to play around with the sliders and let me know what you observe. Hello everyone, I encourage you to visit the website displayed on the screen. It's a fantastic tool to explore the concepts behind MRI. By experimenting with the controls, you'll gain a deeper understanding of how magnetic fields and radiofrequency pulses are used to generate detailed images of the brain. I think you'll find it both educational and fun. This simulation showcases how a strong magnetic field aligns protons, and then a radiofrequency pulse tips them, allowing us to measure the energy released as they realign. This forms the basis of MRI, providing incredible insights into the human body. Isn't it fascinating how we can peer inside without surgery? Think about the incredible detail in an MRI scan. It's all thanks to these tiny protons in our bodies responding to magnetic fields and radio waves. It truly is amazing. I invite you all to try out this interactive simulation for yourselves at BioniChaos.com/MRI_sim/ and share your feedback. What do you find most interesting or surprising about it? So what you're seeing in the proton spin simulation are individual protons, each with its own magnetic moment, acting like tiny spinning magnets. The B0 field is the strong static magnetic field of the MRI scanner, which aligns these protons. The RF pulse, on the other hand, is a brief burst of radiofrequency energy that temporarily knocks these aligned protons out of alignment. When the RF pulse is turned off, the protons relax and return to alignment, releasing energy that is detected and used to create the MRI image on the right. This process is repeated for different slices, allowing us to build up a detailed 3D image. It's amazing to see how the protons react to the RF pulse, isn't it? The stronger the RF pulse, the more the protons tip, leading to a more defined signal for the MRI image. You can even see how individual brain slices contribute to the overall picture. What are your thoughts on how changing the RF pulse intensity affects the final image? For those interested in seeing how these principles apply to a real brain, check out our MRI Synthetic Brain Generator at BioniChaos.com/MRI_synth/. You can explore different brain slices and even toggle on Show Pathology to see how various conditions appear in an MRI. It's a fantastic way to visualize the output of what we've been discussing. What do you think you could learn by exploring this simulator? While both applications are designed to be engaging, the first simulation you saw focuses on the fundamental physics of how protons behave in a magnetic field, providing a foundational understanding. The second, the MRI Synthetic Brain Generator, shows the real-world application of those principles by generating images of a brain. The realism comes from the complexity of the data being represented. The synthetic brain is a simplified model, but it effectively demonstrates how MRI scans capture anatomical details. This simulation you're currently viewing, the Interactive MRI Simulator, is like a bridge between the two. It allows you to directly manipulate the field strength and RF pulse to see their immediate impact on proton behavior, and, in turn, how that influences the resulting image. Does this help you understand the differences better? Let's delve a bit deeper into what's happening. The B0 field, set here at 1.8 Tesla, is what initially aligns those tiny proton spins you see on the left. Think of it like a bunch of compass needles, all pointing in the same direction because of a strong magnet. Now, when we apply the RF pulse, currently at 73 degrees, it's like a quick, precise nudge that temporarily pushes these compass needles away from their alignment. It's the subsequent relaxation of these protons, as they realign with the B0 field, that gives us the signal to construct the MRI image. The different rates at which protons relax in various tissues allow us to differentiate between them in the final image, revealing anatomical structures and potential abnormalities. Does that clarify the process for you? This simulator visually represents the core concepts of MRI. It shows how the magnetic field aligns the protons, and then how the radiofrequency pulse excites them, causing them to re-emit signals that are used to create the image. It's a fundamental demonstration of how we can observe the invisible world of atomic nuclei to get a picture of the inside of your body. What part of the process do you find most intriguing? And you're right, the best way to truly grasp how MRI works is to experience it firsthand. So I highly encourage all of you to visit bionichaos.com/MRI_sim/ and play around with the settings. See how adjusting the magnetic field strength and the radiofrequency pulse intensity changes the proton behavior and the resulting MRI image. What observations do you make when you adjust these parameters?
There is a human in the loop. We're actually trying to fix another simulation that we have a bit better. I don't know why it takes so long to load the data. Okay, just a conversational response without modifying the code. Can you explain why the web application is a bit too heavy on the browser?
The web application is heavy on the browser mainly because it generates and processes a large 3D synthetic MRI dataset entirely in JavaScript, directly in the browser. Here are the main reasons for the heaviness. High-resolution 3D data. The app creates a 256 by 256 by 256, over 16 million voxels, 3D array for the synthetic brain, which is a significant amount of data for a browser to handle in memory. Complex data generation. The synthetic brain is generated using computationally intensive algorithms like fractional Brownian motion, FBM, and simplex noise, with multiple octaves and layers for anatomical realism. This is all done on the main thread, blocking the UI and causing slowdowns during generation. No web workers. All calculations run on the main JavaScript thread, so the browser UI can become unresponsive while generating or updating the data.
Okay, I don't mind not having the web workers. I don't think they change much. I want a single HTML file with all the JavaScript in it, but can we address the other points working?
The main reason the application feels heavy is that it generates a very large 3D dataset, 256 by 256 by 256, all at once, which is a lot of data for a browser to handle in memory. The synthetic brain model uses complex noise functions and multiple layers of computation for each voxel, so the initial data generation is computationally expensive and can cause the browser to freeze or lag.
Okay, so for the 128, can we add a toggle button or a drop down or something? How would you recommend going about it?
A simple and user-friendly way to let users choose between 128 superscript 3 and 256 superscript 3 resolution is to add a drop-down menu or a toggle button near the other controls. A drop-down labeled resolution with options for 128 and...
Okay, that actually sounds good. Can we add that and make it lower by default? Can we have like three different, like very low, medium, and very high, and just select the medium by default, the medium value? Can you just modify the code, then let me know in conversational style what changes were made?
I've added a resolution drop-down to the controls, allowing users to select between very low, 64, medium, 128, and very high, 256, resolutions. The app now defaults to medium, 128, which is less demanding than before. When you change the resolution, the brain data is regenerated at the new size and the view updates automatically.
Okay, that's fine. That is looking good. There's just one problem. They say things are distorted at the medium and very low resolution, and they work correctly. They appear correctly on the canvas only with the very high resolution. For example, the pathology, whatever thingy that we see in the medium resolution is essentially outside the brain. Can you check and suggest a brief fix to the problem?
The distortion and misplacement of features like the pathology at lower resolutions is happening because the code uses fixed offsets, like center plus 40, center plus 25, etc., for positioning anatomical.
Okay, that sounds legit. Can we actually fix the code to address that? I'll be testing it straight away. Okay, when we add pathology.
The code is now fixed so that all anatomical and pathology offsets are proportional to the selected resolution. This means the simulated pathology and other features will appear in the correct location and scale, no matter which resolution, very low, medium, or very high, you choose. You should now see consistent and correct anatomy and pathology placement at all settings.
Still generating for some time the image. This lower resolution does help a lot. Just one minor change. When we click Show Pathology, we don't immediately see it. We actually need to scroll. It's on slice 49, whatever, 50, 47. So can we actually make sure when we hit the Show Pathology, the correct slice is shown? Do you know what I mean? It's actually
Now, when you click Show Pathology, the simulator will automatically jump to the slice where the pathology is centered for the current view, axial, coronal, or sagittal. This means you'll immediately see the lesion without needing to scroll manually. The behavior is consistent for all resolutions and views.
It does work better. So when we in axial view, I hit Show Pathology, it's showing me the correct slice. But when we in coronal view, I hit Show Pathology. It also works. When we in sagittal, I hit Show Pathology. It also works. Yes, that's actually great. Thank you very much. Hey, can you just do a conversational overview? I don't mind you being critical and fun as well, but it's working pretty well. It's working pretty well. Just deploy.
You started by asking why your MRI Synthetic Brain Generator web app was heavy on the browser. I explained the technical reasons, mainly the large 3D dataset and real-time computations. You then requested a resolution toggle to let users pick between different dataset sizes, very low, medium, very high, defaulting to medium. I implemented this as a drop-down and ensured all anatomical and pathology features scaled proportionally, fixing the issue where features were misplaced at lower resolutions. You asked for the documentation at the bottom of the page to be updated to reflect the new features and controls, which I did. Finally, you wanted the Show Pathology button to automatically jump to the relevant slice for the current view, axial, coronal, sagittal. I updated the code so that toggling pathology now jumps to the correct slice in all views. Throughout, you provided clear feedback and tested each change, confirming when things worked as expected. The process was iterative and focused on usability, performance, and educational clarity. All your requests were addressed, and the code now offers a more robust, user-friendly, and accurate simulation experience. If you have further improvements or want to push the realism or interactivity even more, just let me know.
Hey everyone! So on the screen right now, we've got a cool MRI simulation going on. On the left side, you can see these little protons spinning around in a magnetic field. And on the right, we're seeing the MRI image that's created from that. You can adjust the magnetic field strength and the radio frequency pulses to see how it affects the image. Pretty neat, huh? It's like seeing how the technology actually works right before your eyes. Isn't it fascinating to see the science behind MRI technology? You can see how those protons react and how it helps us create these detailed images. I highly recommend you guys check out this interactive simulator for yourselves. Play around with the settings and see what you discover. It's a great way to understand how this amazing medical imaging works. Let us know what you think. What part of the simulation do you find most interesting? All right. Buckle up, folks. Let's dive a bit deeper into the technical wizardry happening on the screen. So, on the left, we're seeing the proton spin simulation. Those little arrows represent the magnetic moments of hydrogen protons in a strong magnetic field, aptly called B0 field. Notice how most of them are aligned, right? That's because the strong magnetic field influences them. Now, when we apply that RF pulse, the radio frequency intensity that you can adjust, it's like nudging those protons, throwing them off their alignment. And as they relax back, they emit signals which are then used to create the resulting MRI image on the right. Isn't that incredible? We're literally using physics to see inside. What part of this process seems the most mind-blowing to you? And can you imagine the impact this has on medical diagnosis? It's like having a superpower to peek inside the body without surgery. So what do you think? Pretty cool stuff, huh? So diving even deeper, that B0 field strength you see there, measured in Teslas, is super important. The stronger the field, the more aligned the protons become, and generally, the better the image quality. And that RF pulse intensity you're tweaking determines how much those protons get excited. It's like fine-tuning a radio signal to get the clearest picture. And have you noticed the brain slice slider? That allows us to view different cross-sections of the simulated brain. It's like taking slices through the brain to see different parts in detail. How amazing is that? It's like having X-ray vision. Can you imagine the challenges the scientists faced in developing this technology? It's truly remarkable. And think about the future possibilities. What other medical breakthroughs could come from advancements in imaging technology? This simulator is just a glimpse into the incredible world of medical science. Keep exploring, keep asking questions, and keep being amazed by the wonders of science. We love to hear your thoughts and discoveries. While textbooks and lectures in medical schools and biomedical engineering programs provide essential theoretical knowledge, this interactive simulator takes it to another level. Instead of just reading about the principles of MRI, you can actually manipulate the parameters and see the immediate impact on the imaging process. It's like having a virtual lab at your fingertips, allowing for a more practical and intuitive understanding. It bridges the gap between theory and application in a way that traditional methods sometimes struggle to achieve. Wouldn't you agree that hands-on experience, even in a simulated environment, makes a huge difference in learning? And the best part is, everything we've been exploring is available right here on this website. Right now, you should be seeing the main page for BioniChaos Biomedical. It's a fantastic platform with various interactive simulations for biomedical science and education. Besides the MRI simulator we just talked about, you can explore other things like an MRI Synthetic Brain Generator, where you can examine different brain structures, and even a simulation on eigenfaces, the science behind facial recognition. How cool is that? This website is a fantastic resource for students, educators, and anyone curious about biomedical science. Don't just take my word for it. Go explore it yourself, and let us know which simulation you find the most interesting and what new things you learn. It's like having a whole science museum at your fingertips. And who knows what amazing discoveries you might make. So what are you waiting for? Dive into the world of biomedical science and prepare to be amazed.
Okay, so you heard the robot. We published four tools today. Quickly go. Should only take a second. We have this optical illusions. Obviously, optical illusions are highly relevant to neuroscience, behavioral neuroscience, so on and so forth. So you can check this one out. Just pop the link in the chat or the description of the video. Hopefully we'll have a good video out of it later on. We also have eigenfaces. Yeah, making this one before. It will do a reconstruction of your face. Can do actually a better one. We'll do 4 eigenfaces, then you can automate your face. It will move each slider one at a time. So go check this one out as well. What else we got? We got this MRI. So you can go through the slices. Yes, we had some problem before. We were loading too many slices. Now we have an option to change your resolution. So it kind of depends on what your machine can do, because everything is running in the browser. You can show pathology. It will show you this thing. What should be showing it in every view. Anyhow, it does work. You can change your resolution as well, so go check this one out as well. Pop the link. And the last one is the one the robot was talking about before. You can choose your strength of the magnetic field. Adjust your, well, that's still in demo mode. So you can do it. What? Right. We can see the spin is recovering slower or faster depending on the strength of the magnetic field. You can see the reconstructed image, a bit low resolution because there's a lot going on this page, so it will go through the slices quickly. Each will show 10 slices. So yeah, play around with this one as well. I think if you don't interact with the page for a while, it will go into demo mode. Demo mode, demo mode. Or do you actually need to click play demo? Let's reload the page for a sec. Now it's going into demo mode on page load. So yeah. So it's working well. Oh, and you have to interact with the page for the sound to work. So now you'll have this weird sound as well. That doesn't actually contribute much, but yeah. Have you been in an MRI machine? What sound does it make? And we have way more tools coming shortly as well. So everything we do is available on BioniChaos.com. We have Patreon page if you want to support this project. You can support it on YouTube itself. And I'll see you next time. Let me know if there's any questions. Pop them in the chat. Bye.